Okay, so here are the solutions to the vectors in the plane section. So the first three problems are asking you to find the component form and the magnitude of vector v. So to find the component form, and we'll do it both ways, there's the kind of the coordinate pair versus, and there is the I and j unit vectors. So we'll do both of them. So let's call this, so the initial point is point P and the final point is point Q. So we have vector PQ. And all you do is you just subtract the final coordinate, x coordinate, from the initial x coordinate. Put a comma. I'll give you your x component. You take the y component of the final point and then subtract that from the y component of the first point. Notice I'm not using brackets, I'm using these angled. I'm not using parentheses, but angle brackets. So you have 16 minus the negative 1, which should 15 minus the negative 1 should be 16, and 12 minus 5, which is 7. So that's one way of representing the vector PQ. Or you can put it in notation where you have 16i plus 7j, where I is the unit vector in the x direction and j is the unit vector in the y direction. Okay, so the rest of them are the same kind of deal here. So you take the x component of the final point, subtract the x component of the initial point, y component of the final point minus the y component of the initial point. So 8 minus 1 is negative 9. Negative 9 minus 3 is negative 12. Now I forgot to give the magnitude. We'll do that. We'll come back and do that in a second. And then finally, the last problem. So you've got 5 minus a negative 2 and negative 17 minus 7. Five minus a negative 2, negative 17 minus 7. So 5 minus a negative 2 is the same as 5 plus 2, so that's 7. And negative 17 minus 7 is negative 24. Okay. Now let's go ahead and do the magnitudes. Now the magnitudes you show by putting these two vertical lines. It's kind of like an absolute value, but you have two of them. So we take the x component, square it, and add the y component, square it, take the square root, and typically these are going to be, they usually don't end up being complete squares. But if they do, that's fine, but most of the time they don't. So I'm just going to leave it as a square root. So you have 16 squared plus 7 squared, which is 305. So you get the magnitude as the square root of 305. Now if there were any complete squares that you could rewrite this as a multiple of, then you could simplify it, but I doubt there's anything that works out. It's not divisible by 3. It is divisible by 5, but you'd have to be able to divide it by 25, which obviously is not going to work because 300 is divided by 25, so 305 is definitely not going to be. So I think that's the answer. Okay, so that's the magnitude for part 1. For problem 2, the magnitude of the vector is going to be equal to the square root of negative 9 squared plus negative 12 squared. And usually what I do is I just square 9, because I know that if I square a negative sign, I'm going to get a positive number, so it just saves me time. So 9 squared is 81. 12 squared is 144. Add those together. You get 225. Square root of 225. And the magnitude is always positive because you're taking the square root of a number, which has to be positive because there's no domain for the squared function is positive, besides the fact you square any numbers inside, which make everything positive. Now in this case you could rewrite this because 225, if you take 225 divided by 25, you'll get 9. So this is 9 times 25. Interesting. Okay. Well, both of these actually are perfect squares, so that's the same as the square root of 9 times the square root of 25. The square root of 9 is 3, the square root of 25 is 5, so you get 15. So it just happens that's one of those. And that makes sense because you think usually a lot of times these when they work out is you have like a 3, 4, 5 situation. 3 squared plus 4 squared equals 5 squared, or 3, 4, 5 triangle. You'll notice these are multiples of these. So 3 times negative 3 is negative 9. 3 times negative 3 times 4 is negative 12. So that's why it ends up being 3 times 5. Okay. And then the last one, number 3 here, we have the magnitude of PQ is equal to the square root of 7 squared plus negative 24 squared. This actually may be another one of those cases. I think I just arbitrarily picked these, but I just said it didn't happen very often. And it doesn't. It's just I ended up, we'll see what happens here. Yeah, actually it does. So 625, and if you take the square root of 625, you get 25. So the magnitude of the last one is 25. Okay, so that's the first 3 problems. Next one is to do vector addition and subtraction and multiplying by a scalar. So that what they're asking us to do here is to perform these 2 operations and then multiply each one of these by a scalar and then do the operation associated with the resulting thing. So here we have u plus v. You notice that there's 3 ways of representing vectors. One is to use an arrow, so that's vector. Another one is to do this little hat thing, which is a little more compact, and then you can use bold if you're typing something. So vector u is 5, negative 5, 3, and we add that to vector 1, 5. And when you add vectors, you just add the components. So it's going to be 5 plus negative 5 plus 1 and 3 plus 5, and you get negative 4, 8. And you could do that. You could skip this step if you do it correctly. That's what I would do. I'd say negative 5 plus 1 is negative 4. 3 plus 5 is 8. Okay, now to do u minus v, what you do is that's the same as u plus negative v. So what I would do is I would write out u, which is negative 5, 3, and I would add the additive inverse of that. So what you do is you change these to negative signs. So this is negative v, and then I add them together. So you got negative 5 plus negative 1 is negative 6, and negative 3 plus negative 5 is going to be negative 2. You could also think if I take negative 5 subtract 1, I get negative 6, and 3 subtract 5, I'd get negative 2. So now why would I do that? Well, it turns out if you do it graphically, then it makes more sense to do this. Subtraction is taking the vector, switching the arrow from one side to the other. Okay, I haven't sketched them yet, so I'll go back and sketch them in a second. Okay, so now what we have is okay, I'm having some cursor issues here, so let me just pause for a second. So the last one is we have 2u minus 3v. So the way we would do that, 2u minus 3v, we would take vector u and double everything. So we'd have negative 5, we'd change that to negative 10, and 3 we change to 6. So that's double vector u. And we'd subtract 3 times vector v. So 3 times 1 is 3, 3 times 5 is 15. And again, I'm going to rewrite this subtraction as an addition and change these to negatives inside. So here you have negative 10 plus negative 3, so that's negative 13, and then 6 minus 15 is 9. So that's your final answer. Okay. Now it's ask us to plot these, so we'll put them on one graph. I can spell graph right. Still spelled it wrong. G-R-A-P-H. Now the first two are less than 10, but the third one is greater than 10. So what I'm going to do is I'm going to go to 20 here, go to negative 20, 20, negative 20. So we have 10 each, and that's the wrong place. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 10. Okay, so this is 10, 10, negative 10, negative 10. Okay. So we're going to draw these in the standard position, which means we go from the origin, and then we go to the point, which is, in this case, negative 4, 8. So that's u plus v. The second one here is negative 6, negative 2. So that would be negative 6, negative 2. And then the final one is negative 13, which would be there, 9. So it would be right there. So those are the three vectors. This is vector, this is u plus v, this is u minus v. This one is 2u minus 3v. Okay, next one, same kind of deal. So we have u plus v. So that's 2 comma 7 plus negative 2, negative 3. So we have 2 plus negative 2, which is 0, and 7 plus negative 3, which is negative 4. So that's the answer for the first one. U minus v is 2 comma 7 plus, change the signs here, 2 comma 3. So subtracting this is like adding the inverse, additive inverse. So now we add them together, so you'll get 4 comma 10. Okay, so that's u minus v. And then finally 2u minus 3v. So we'll take u, which is 27, and we'll double that. So 4, 14. And I'm going to go ahead and change the signs here as well. So if I multiply this by negative 3, I'll get positive 6. And if I multiply this by negative 3, I'll get positive 9. So this is negative 3v. So I'm adding negative 3v. Okay. And then I add the terms together. So I get 10 comma 23. So that's 2u minus 3v. So let's plot those. Yeah, the last one's a little bit out of the scale. So what I'm thinking of doing is if I go see, if I go by 2's, I'll get to 20. If I go by 3's, I'll get to 30. But 3's, I just don't like that as an increment. It's harder to figure it out. So we'll just do 40. The things are going to be kind of short. The first one's going to be kind of short. So this is this would be 2, 4, 8, 12, 16. No, it's not right. It's going to be 8, 16, 24, 32, 40. Okay, so that's the increment. So I'm just going to put tick marks here on the other labels, the other axes. Okay, so let's draw the first vector. So it's 0, comma 4. That's right up there. Yeah, I was trying to decide whether to do u and v as well, but I don't think so. Okay, next one is 4, comma 10. So we go 4, this would be 8, 12, so this would be 10 right there. So it's 4, comma 10. And the final one is 10, which would be here. So this is 8, 12, 16. So 10 is halfway between the tick marks. 23. So this would be 24. So 23 would be right there. It's interesting. Looks like it's almost the same direction as this other vector. It's not quite. Does that make sense? Something doesn't seem right. Oh. Let's undo what I just did here. This one actually is too long. Should only go to there. So each small increment is 4. And then I've got this one was 4, comma 10. So this is 8, 12, 10. So 10's actually there. So 4 here, and then 4, 8, 10. And then I've got one that's 10, 23. So that's 10 is here, and you'd go 8, 16, 20, 23. So they're not exactly, because what you look for is kind of the ratio here. If you multiply this by, to get 10, you'd multiply 4 by 2.5, I think. So 4 times 2.5 is 10. And if I took 10 times 2.5, I'd get 25. Yeah, so it's just looking at the proportion of each one of those. Let's double check, make sure that I didn't do anything wrong here. So you've got U. Let's go back here, double check. So we've got 2,7 plus this, so you get 0 and oh, there you go. That's why the problem right there. That should be 4. I don't know how I got that. We'll fix that in a second. Then we got this minus that. So I changed the sign. These add together 4. These together 10. That works out right. Then I've got 4 14. So I'm doubling those two. Then I'm tripling those, which gives me that. Changing the sign, adding them together, gives me 10, 23. Okay, so this was actually the right answer. I don't know. So I did it right on the drawing. I did it right, but it didn't correspond with that. So anyway, those are the correct answers now. And then finally, this is in unit vector notation. So the way we do that is, U plus V is going to be negative 2I plus 4J. So that's U plus 3I minus 1J. I put a 1 in here just so you know. So now when you have this unit vector notation, you just add the components together. So you'd have negative 2 plus 3, which would give me 1. And 4 plus negative 1 would give me 3. So I'd have, and I would just write that as I plus 3J. Okay. Now U minus V is going to be negative 2I plus 4J plus, and I'm going to change the sign here, so this becomes negative 3I plus J. So again, adding the components together, we get negative 5I plus 5J. So that's U minus V. And then finally, 2U minus 3V. So again, I take this vector and I multiply by 2, so I'd get negative 4I plus 8J. And I'd add to that and multiply by negative 3. So I get positive 9I minus 3J. And then we add these together. So negative 4I plus 9 give me 5I, and 8J minus 3J is 5J. Okay, so that's 2U minus 3V. Okay, so let's plot those. Let's add a page. Put my graphing up there. These are all less than 10, the components, so I'm gonna draw the scale. So we go from negative 10 to positive 10. So the first resultant vector is 1, 3. So 1 in the x direction, 3 in the y direction. Okay, so that's the first one. The next one is negative 5I, 5J. That goes there. And the final one is 5I, 5J, which goes right there. Okay, next one, find the unit vector in the direction of the given vector. So all you have to do for that, and we'll call the unit vector u. That's why I called everything here v. So we'll call u the unit vector, and the unit vector is going to be equal to the x component of the u vector divided by the magnitude of the u vector, and then comma the y component of the u vector divided by the magnitude of the u vector. So all we need to do is find the magnitude of u, and that's equal to the square root of 2 squared plus 6 squared. So that's 36 plus 4, square root of 40. That's 2 times the square root of 10. Because 4 squared, 2 squared is 4. So that if I bring this inside, it becomes, instead of 2 times the square root of 10, it becomes square root of 4 times 10. Okay, so then the unit vector u is 2 divided by, which is the x component, divided by 2 square root of 10, and the y component is 6 divided by 2 square root of 10. So, we could simplify this. You get 1 over the square root of 10, 2's cancel out, and 3 divided by the square root of 10. And then you would get the square root out of the denominator. So you'd have the square root of 10 over 10, and you'd have 3 times the square root of 10 over 10. So that is the unit vector. And what that means is it is in the same direction. It's the same direction as the original vector, but it has a length of 1. If I take this squared plus this squared, I'll get 1. Take the square root, I'll still be 1. Okay, next one. Again, what we need to do first is find the magnitude of the vector v. Did I show that as v? Oh, yeah, I messed up over here. I should have made this. These all should be v's. I don't know why I did that. So this should be v sub x. This should be magnitude of v. Okay, so the unit vector is the x component of v divided by magnitude of v. The y component of the unit vector is the y component of vector v divided by the magnitude of v. This is right. This is the unit vector. This is the magnitude of v. Okay. Make sure I get that right. Okay, so what we do here is we take the square root of -3 squared plus 7 squared. So that's the square root of, we got 49 plus 9, which is 58. And I don't think you can simplify that because you can't divide by 4. And nothing else jumps out at you. Okay, so and the unit vector is equal to the y component, x component divided by the magnitude, and the y component, the unit vector, is going to be the magnitude of the vector divided by, the y component divided by the magnitude of the vector. And so what we do is we multiply and divide by the square root of 58, and you would get that. So that's your answer. Okay, next one. So this is in unit vector notation, but we do the same thing. This is number 9. So the magnitude of vector v is equal to the square root of 5 squared plus -2 squared. So 5 squared is 25, -2 squared is 4. Add them together, you get 29. So the unit vector, now what we do here is we take the unit vector notation, we divide the x component by the square root of 29, and we take the y component and divide by square root of 29, and then we again multiply and divide by the square root of 29. And that's your final answer. Okay, next one is find the vector v with the given magnitude in the same direction as u. So you kind of go the opposite direction here. The procedure is we're going to find the unit vector associated with this, and then if you multiply the unit vector associated with this vector and multiply it by the magnitude of v, you'll get the vector v. So first step, now since we've already used u here, I'm going to let w be the unit vector. So that's the unit vector associated with vector u. You're going to take so what is the magnitude of u? Well, it's going to be equal to the square root of 2 squared plus 5 squared, which just was the same as the previous problem, 29 square root of 29. So the unit vector w is 2 divided by the square root of 29, and the y component is 5 divided by the square root of 29. So that's my unit vector. And vector v is equal to the magnitude of vector v times the unit vector w. So that's going to be equal to 3 times 2 divided by the square root of 29, comma 5 divided by the square root of 29. 3 times 2 is 6. I get 6 divided by the square root of 29. And 3 times 5 is 15. 15 divided by the square root of 29. And I'm going to go ahead and multiply and divide by the square root of 29 to get the final answer. So this is vector v. So remember, the way it works is I define the direction of vector u by finding the unit vector. The unit vector has a magnitude of 1 as far as the distance. But if I then take that unit vector w and multiply by the magnitude of v, that will give me 3 times the unit vector will give me the actual vector v, which has the same direction as vector u, but it's 3 times as well, it's not 3 times as long. It's 3 times as long as the unit vector, but it'll have a magnitude of 3. Okay, same thing for number 11, except I'm in unit vector notation. So what did I say? The first thing I need to do is to find this unit vector w, and that's going to be equal to the x component of u divided by the magnitude of u times I plus u sub y divided by the magnitude of u times j. So we need to calculate the magnitude of vector u, and that's going to be equal to the square root of negative 1 squared plus 3 squared, which is the square root of 10, 9 plus 1. So my unit vector w is going to be equal to negative 1 divided by the square root of 10 I plus 3 divided by the square root of 10 j. I'm going to go ahead and, before I waited to rationalize this thing, but I'm going to multiply and divide by the square root of 10 here, and again here. Okay, so that's the unit vector. So my vector v is equal to the magnitude of v times the unit vector w. So I get the magnitude is 5, so I'll get 5 times negative the square root of 10 over 10 I plus 3 times the square root of 10 over 10 j. And then finally multiply the 5 out, so you get negative 5 the square root of 10 over 10 I plus 15 square root of 10 over 10 j. So that's your answer. It's kind of like when you're dealing with lines and you have one line, you're trying to find the equation for the other line. You know, you find the slope of the line. So the unit vector is kind of equivalent to defining a slope. Okay, find the component form of v given its magnitude and the angle it makes with the positive x-axis. Sketch v. So let's we'll sketch it after we figure it all out here. So there's two ways you can do this. One is, it's like the last problem. Let's let u be the unit vector in this case, and u is equal to the cosine of theta I plus the sine of theta j, or we could say u is equal to cosine of theta comma sine of theta, where this theta has to be with respect to the positive x-axis. Let's use unit vector notation. So we'd have the unit vector that's in the same direction as this directional angle is going to be equal to the cosine of 72 degrees. Make sure your calculator's in in degrees. So you take cosine of 72. So I get 0.3090. Well, yeah, I didn't fully write this thing out. So it's the cosine of 72 degrees I plus the sine of 72 degrees j. So the cosine of 72 degrees is 0.309, and the sine of 72 degrees is 0.951 j. So that's the unit vector. So to find the vector v, I take the magnitude of v times the unit vector. So that's going to be 5/2 times 0.309 I plus 0.951 j. And so let's just multiply those out. 0.309 times 5/2. You get 0.773 I. And if you take 5/2 times 0.951, you get 2.38 j. So that's your answer. We'll sketch. Well, let's go ahead and sketch it. Okay, this is going to be a short vector because I'm going to define the limits of the coordinates system there, but we go 0.7 something this way and 2.38 that way. So that's just an approximation. This angle here, 72 degrees. Okay. Let's go back and do the next one. Same kind of deal. So the unit vector is the cosine of 210 I plus the sine of 210j. Now 210 is going to be in the third quadrant. So I should have negative. These both should be negative. So you have the cosine of 210, which is negative 0.866. And I just said it was negative. I put a positive sign here. The sine of 210 is negative 0.5. So that's the unit vector in the direction of 210 degrees. So vector v is the magnitude of v times the unit vector. So you get 3 times negative 0.866i minus 0.5j. And if you multiply that out, 3 times 0.866 is 2.60i minus 1.5j. So let's draw that. Negative 2.6, negative 1.5. Negative 2.6, negative 1.5. So that's about right there. And this angle here should be 210 degrees. And reference angle here would be 30 degrees. So that looks about right. Okay, so that's the second problem. And then you've got the last problem. So again, the unit vector is the cosine. What we'll do, we'll use the other notation here. So it's going to be the cosine of 123, comma, sine of 123. Now that's in the second quadrant. So second quadrant, cosine's negative, sine's positive. Cosine of 123 should be negative, which it is, negative 0.545, and the sine of 123 should be positive, 0.839. So that's the unit vector. The vector v is equal to the magnitude of v times the unit vector. The magnitude is 5 multiplied by the unit vector. So 5 times negative 0.545 is negative 2.73, and 5 times 0.839 is 4.20, negative, positive. So this is going to be in the second quadrant, 2.7 and 4.2. So you go negative 2.7, positive 4.2 would be about right there. And this angle here is 100 and whatever it was, 23 degrees. Okay. Okay, next thing is, it says find the component form of the sum of u and v with directional angles theta sub u and theta sub v. So what we're going to do is we're going to break up the vectors into component form, and then we'll add the two components together to get the resultant vector. So this is 15. So vector u is going to be equal to the magnitude of vector u times the unit vector associated with that directional angle. So I'm just writing it out here. So this is the magnitude of u times the cosine of 70i plus sine of 70j. So the magnitude is 5 times cosine of 70 degrees I plus sine of 70 degrees j. And let's just multiply that on our calculators. 5 times the cosine of 70 is 1.71 I, and then 5 times the sine of 70 is 4.70 j. So that's u. Same thing for vector v. Vector v is equal to the magnitude of vector v times the cosine of 120 degrees I plus the sine of 120 degrees j. So v is 4. 4 times the cosine of 120 I plus the sine of 120j, and this is in the second quadrant, so you should get a negative I component and a positive j component. So 4 times the cosine of 120 is negative 2, so it's negative 2i, and then 4 times the sine of 120 is plus 3.46 j. So that is vector v. Now let's use r. R is the resultant vector. That's the sum of the two vectors. So we have 1.71 I plus 4.70 j, so that's u, and we add negative 2i plus 3.46 j, and at this point you just add the components together. So you have 1.71 minus 2, you get negative 0.29i, and then we get 4.7 plus 3.46, and we get plus 8.16 j. So that's the resultant vector in component form. So that's the final answer we're looking for here. And we'll do the same thing for the next problem. So for number 16, u is equal to the magnitude of u times the cosine 30 degrees I plus the sine of 30 degrees j. U is 12. So we take 12 times the cosine of 30, which is 10.39 I. And you take 12 times the sine of 30, which should be 6 j. Okay, so that's my u vector. Take the magnitude of u times the unit vector in the direction of specified. Okay, so same thing here for v. Magnitude of v times the cosine of 65 degrees I plus the sine of of 65 degrees j. So that's 9 times the cosine of 65 times I plus the sine 65 times j. So 9 times the cosine of 65 is 3.80 I. And 9 times the sine of 65 is 8.16 j. So that's vector v. And to get the sum, u plus v, we just take the two vectors, 10.39 I plus 6j, that's vector u, and add that to 3.80 I plus 8.16 j, and then you add the components together, 10.39 plus 3.8. I'm just going to round it off to 1 decimal point, 14.2 j, and then 6 plus 8.16 is 14.2. How about that? That was just a coincidence. I didn't mean that to happen. Okay, so that's the resultant vector in component form. Okay, so we got 3 problems left now. One is to use the law of cosines to find the angle between the vectors. So let's just kind of sketch what this thing looks like. Doesn't have to be exact, but you're going to have one vector like that, because it's going to have 1 and 1, 1 and 1. And then you're going to have a second vector, which is 2, negative 3. So that's going to be somewhere down like that. And it's going to be close to 90 degrees, but not exactly. Approximately 90 degrees. It's going to be closer to 90 degrees than it is to 0. So the method that's used in this section to find the cosine of the angle is that you what do you do here? So let me hold on just a second. Got to think about this for a second. Make sure I don't do it the wrong way for this particular section. Okay, so what I've drawn here is, this is vector v, this is vector u, this would be the resultant vector. And you can also connect them together like this. You create this triangle. And so the angle we're looking for is this angle here. So if we actually don't need this resultant vector in here, because you've got two sides, and you don't need the, so actually I'm drawing this wrong, I think. Need this length of that vector. So what the heck is that vector? So yeah, I guess there's one way you could do it is find this angle here and this angle here, and then just add them together. That would give you the angle between the two vectors. That might be what they're looking for you to do here. So, so let me kind of expand that now that I had a chance to think about this. There are other ways of doing this that are easier. So what I'm thinking is, if you calculate this angle, this would be theta for v, and this would be theta for u. Now this one will be a negative angle, but we can just take the absolute value of it and add those two together, and that'll give you the, well, but it says use the law of cosine, so I do have to use the law of cosines. Okay, let me pause again. Okay, I'm just going to do it the way. So if we create a vector that goes from here to here, it's not the sum of the two vectors. It actually ends up being, if I take this vector and take the negative of it, so I change the direction, and then I move this vector, which is just the negative of it, if I move it down to here, then the resultant vector associated with basically u minus v, so this is u minus v, is that vector. So if I subtract these two vectors, that's probably why they did them in the opposite order that you would have thought they would have. You get this vector, and you get this vector, and then I can find the length of this vector. I can find the length of this vector and this. I have this length of this vector, which is vector v, and I get the length of this vector, which is vector u, and I have the length of this vector, which is u minus v, and then I can use the law of cosines to solve it that way. Okay, so what we need to do is calculate u minus v. So that's going to be 2I minus 3j minus, I can write these as parentheses, 2I minus 3j minus I plus j. So that becomes 2 minus 1, so that's 1I, and negative 3 minus 1, that becomes negative 4j. Okay, so that's u minus v. And what we'll do is we'll call this angle A. So this is side A, this is side B, this is side C. And what the law of cosine says is that the cosine of A is equal to b squared plus c squared minus a squared divided by 2bc. So we need the lengths of these. So the magnitude of v is the square root of 2, because 1 squared plus 1 squared, that's 2 square root of 2. The magnitude of u is going to be 2 squared plus negative 3 squared, so that's 9 plus 4, which is 13, so I've got the square root of 13. And down here, the magnitude of u minus v is equal to the square root of 17, because that's 1 squared plus 4 squared. So 1 plus 16, square root of 17. So now if I go up here and substitute, I'll get the cosine of A is equal to B, which is this length, which is that. So it's the square root of 2 squared, plus length of C, which would be the magnitude of vector u, which, so I'd have the square root of 13 squared, and I'd subtract the square root of 17 squared, all divided by 2 times the square root of 2 times the square root of 13. So I get the cosine of A. So 2 squared is 2. Square root of 2 squared is 2. Square root of 13 squared is 13. Square root of 17 squared is 17. And I divide by 2 times the square root of 2 times the square root of 13. And that number is, so you get 2 plus 13 minus 17, that's negative 2, divided by 2, divided by the square root of 2, divided by the square root of 13. And I get negative 0.196. So the cosine of A is negative 0.196, and to find A, that's going to be the inverse cosine of negative 0.196. So the inverse cosine is 101.3 degrees. And you can see the angle here is close to 90. I said it was going to be close to 90. Now the other way of solving this problem, just to double check our answer, is you could find the directional cosine associated with this, and I'm just going to do this to prove that it's right. You don't need to, you can just listen along. So the cosine of theta sub v is going to be equal to basically 1 divided by the square root of 2, which is the square root of 2 over 2, so theta sub v is 45 degrees, which makes sense because you got 1 and 1 here. And then you got theta sub u, you take, so the cosine of theta sub u is going to be, 2 divided by the square root of 13. And if I take the inverse cosine of that, so I'm take the inverse cosine of 2 divided by the square root of 13, I'll get 56.3 degrees. And I said this angle A, is going to be equal to theta sub v plus theta sub u. So that's 45 plus 56.3, and I get 101.3 degrees, which is what I got over here. So when I saw the problem, I forgot that it said law of cosines, and I was thinking of doing it this way. But to make it into a law of cosines, you've got to create a triangle. And the triangle has to, the opposite side from the angle A has to be this line, which is not the sum of the two vectors, but is the difference between the two vectors. Okay, next we've got three forces with magnitudes of 40, 60, and 35 act on an object at angles of 20, 65, and 110 degrees respectively with the positive axis. Find the direction and magnitude of the resultant force vectors. So what we do here is we're going to change these three vectors, which are in terms of magnitude and direction, into component form, and then we're going to add the components together to get the resultant vector in component form, and then we'll use that to find the magnitude and direction of the final vector. We do this a lot in physics. So I'm just going to kind of show you how to do this. So let's call F1 the 40 units. I didn't give it so let's make it pounds. So you're going to have 40 pounds, that's the magnitude, times the cosine of 20 degrees, I plus the sine of 20 degrees J. Okay, F2 is going to be equal to 60 pounds times the cosine of 60 degrees I plus the sine of 65 degrees J. And F3 is going to be 35 pounds times the cosine of 110 degrees I plus the sine 110 degrees J. So I'll let you multiply those out. I'll give you the answers. 40 times the cosine of 20 is 37.6 pounds I. Then we have 40 times the sine of 20 degrees. That's going to be 13.7 pounds j. Okay, the next one is 60 times the cosine of 65. So I get 25.4 pounds I. And 60 times the sine of 65 is 54.4 pounds j. And the last one is 35 times the cosine of 110. So that's negative 11 point, actually that to one digit, negative 12.0 pounds I plus 35 times sine of 110, 32.9 pounds j. So our final vector, we'll call that r. What we do is we add the x components together to find the x component of the resultant vector. So you'll take 37.6, I'm going to leave the pounds off, well, put the pounds on, 37.6 plus 25.4 plus negative 12.0. So that gives you the x component of the resultant vector. 37.6 plus 25.4 minus 12. So that's 51 pounds, 51.0. Do the same thing in the y direction. So you'll have 13.7 pounds. That's the y component here, plus 54.4 pounds, plus 32.9 pounds. You add those together, 13.7 plus 54.4 plus 32.9 is 101.0 pounds. So those are my x and y components. And we can draw that, sketch it here, x, y. They're both positive. The y component's a little more positive than the x component. So we're going to have this angle, theta, between the positive x-axis and this force vector. It should be on the order of 70 degrees, just guessing. So the way we find the magnitude of r, the r vector, and you do that by taking the square root of the x component squared plus the y component squared. So that's 51.0 squared plus 101 squared. Add those together, take the square root, you get 113 pounds. So that's the resultant vector, the magnitude of the resultant vector. The actual resultant vector would be 51.0 I plus 101.0 j. And the angle is the arctangent of r sub y over r sub x. So you take the inverse tangent of 101 divided by 51. Inverse tangent of 101 divided by 51, and you get 63.2 degrees. Now the final problem is actually a little easier. Here, all we're doing is we're taking this gun that's shot. So what we do is we create a vector to represent this velocity. It's a velocity vector. We'll say it's vector v. And its so that's a vector v. We don't know the magnitude. We do know the magnitude. We know the magnitude of v is 1,000 feet per second. And we know that theta is 12 degrees with respect to the horizontal. So our vector v is just going to be equal to the magnitude of v and then multiplied by this unit vector. So you take the cosine of 12 degrees I plus the sine of 12 degrees J. So that's 1,000 feet per second times the quantity cosine of 12 degrees I plus the sine of 12 degrees J. So 1,000 times the cosine of 12 degrees is 978 feet per second I, and then you take 1,000 times the sine of 12 degrees, 207.9, or just 208, round off to 3 decimals. So you get 208 feet per second J. And so the x component of velocity is 978 feet per second, and the y component of velocity is 208 feet per second. And that makes sense because, you know, this angle 12 degrees is below 45. So when it's a 45 degree angle, they're the same. These are the same value. They still add up magnitude wise to 1,000, but at a lower angle like this, you're going to have a larger x component and a smaller y component, so you can see that's true. And this is also used in physics, is to do what are called projectile problems. And typically you're given the velocity, the muzzle velocity, and the angle, and then you have to break it up into the components and use the components to solve 2 equations separately and then combine the results to get the final answer.